Awesome. So thank you so much for coming to the last session of the day. I recognise that is a great hardship. You'd rather be drinking, sleeping, generally recovering from an adventurous day. So I'm going to talk to you about something a little bit different than the regular mobile talk. I'm actually going to talk about back-end infrastructure. And of course you can be like, well, why is that relevant? Well, it's back-end infrastructure to support a platform supporting millions and millions of cell phones. So my name is Jeffrey Carr. I'm essentially an infrastructure specialist looking after cloud and DevOps technologies at a company called Sailthrough. And what we do is produce a mobile marketing platform for app developers and marketers to target their audience and deliver messaging to them. And my interest there is primarily on supporting the cloud infrastructure and applications that support that product. When I'm not doing that, I do pretty much the same thing at home. I support infrastructure, but it happens to be smart home infrastructure. If that is an interest that you have, we have actually got a meetup here in Wellington, so I'm just going to shill that a little bit. Please do consider coming along. All right, so what is the Sailthrough thing? Well, if you've been around the mobile scene in Wellington for a while, you may know of it under a different name, which is Carnival.io. We were acquired by Sailthrough and now operate under that brand. And ultimately what it is it's software where you can create a message and deliver it to a particular audience. So people interested in discount socks or people interested in cheap flights to Hawaii. And the idea is you use our software to send that message to their phone, they engage with that message, engage with your application, and then we can provide you various analytics and metrics about what they've done based on the engagement or based on the message that you sent them. Now that's like a tiny summary of what it actually is, but we're not so interested in that today. We're interested in what makes this possible. So, given this is a lecture hall, I feel it's appropriate to start with a seminar. This is the one-on-one on push fundamentals. There will be a test afterwards in the class. Attendance is, of course, part of his score. So, getting back to basics. What is push messaging? How does push messaging work? Well, there's two key platforms that we care about, Android and iOS. And strangely enough, there's two key push networks to support that. We have GCM now replaced with FCM, so Fire-based cloud messaging for Android devices. And we have APNS for messaging Apple iOS devices. And I guess before I go into detail, I'll just got a slight rant. Apple, APNS is the acronym. It has a capital S, not a lowercase s, unlike all of your documentation. Although the documentation is not even consistent because you'll see that on the sidebar it says Apple Notification Services with a capital, but then the docs have it with a lowercase s. So, I don't know, I mean, I think a company with a few $1 billion can afford to hire an English teacher.
Maybe it's not like right there, it says underneath. Capital,
Capital, I know. It's interesting. I mean, it's not Apple Push Notifications, it's Apple Push Notification Service. Anyway, I can do 45 minutes about this. All right, so how does this push stuff actually work? Well, regardless of whether it's APNS, and you can see I stole Apple's slide there because it's got lowercase s, regardless of whether it's APNS or Firebase, it works in pretty much the same way. You, the customer or the application developer, send a message via a provider or directly to the gateway. So in the case of our customers, so you, an application developer, would be a customer of us. You'd message our platform, we'd relay your message through to Firebase or APNS, and then those systems magically transform over the internet to appear on the phone. Our case is slightly more complex because we do push marketing. We actually want to know when you engage with the marketing. So we also have a whole bunch of SDK logic in your application, which sends telemetry back to our platform. So this is easy enough on one phone. I mean, imagine a lot of developers here, you've used push messaging before. You've done a curl to Firebase and pushed it out to a phone. Really, really straightforward. It's not that hard to get up and running. But what about when you have a metric shitload of phones? How do you make this scale and how do you support this? You know, it's easy to do one request at a time. It's maybe not so easy to do 10,000 requests at a time. So how do we do this? How do we actually make this function at scale? Well, I'm going to start with the fundamental building block of any modern infrastructure platform, which is containers. And not to be confused with shipping containers, we're talking about Docker. And if you're not necessarily a backend developer, you might have come across Docker or containers before, but the TLDR premise of containers is that you have as a way of packaging an application and all of its dependencies into a single, easy-to-use package that can be redistributed to other computers. And this is really, really popular in the backend space at the moment. Almost every development team I work with uses containers to run their local development environments and in many cases in production as well. Because one of the cool benefits of containerization is you can take what's running on your personal laptop and then push it to a server which could be a virtual machine or an EC2 instance or some other cloud system for running containers. So it's a great model for developing backend software. The only downside of this is at some point it won't scale. A single server running a container works fine for your small startup, for your small application. It may even work fine for a production app in the New Zealand market where there's only, maybe a max of 2 million people who could use your application. But at some point, you're going to have too many users, it can't fit on a single box. So what do we do then? Well, the cool thing about containers is it opens up a whole new world of infrastructure options. And there's a technique we call, or technology we call container orchestration. So the principle behind this is you go, okay, I've got a whole bunch of backends, they're all running in containers, and I need a whole bunch of compute, so I'll just throw all the containers on servers and let the software figure out how to run it. So you don't have to jump onto host 1 and install an application, host 2 and install an application. You just say, hey, I've got these containers, you figure it out. And you're probably familiar with some of these platforms already. So what do? Well, they're responsible for placement of the containers across the complete pool of your servers. And they take into consideration the CPU and memory requirements of your software. So for example, if your backend application requires 2 gig of RAM per copy, and you've got boxes with 3 gig of RAM, it will figure out, hey, I can't fit 2 on one box, I'll spread them across multiple machines, and can launch multiple machines as required. It also provides built-in resiliency to failure. It can handle a crashed backend, it can handle a crashed server. And these platforms typically integrate with cloud providers like Amazon or Azure or Google to drive native features such as load balancers or storage. And you're probably familiar with a couple of the names. So you may have heard of Kubernetes, which is currently like the hot, cool technology that everyone in the infrastructure space is losing their heads about. And yeah, to be fair, it kind of is kind of cool. But you also may have come across Amazon ECS or Mesos. These are like some really popular platforms for this at the moment. So we use Amazon ECS, and we run entirely on the Amazon cloud. And the reason we do this is although it's possible to run container orchestration in an on-prem physical server like traditional data center, for our particular use case, our customer load varies significantly across the course of a day. We have a largely predominantly US customer base of millions and millions of phones. We don't want to buy a whole bunch of physical hardware and run it at peak capacity constantly because, 1.6 terabytes of RAM ain't cheap. I'd rather pay for the 100 gig when it's quiet and then the 1.6 terabytes when it's busy and pay for only what I consume. And the cool thing about cloud technologies is it makes this really straightforward. So that graph on the screen at the moment shows the server count across roughly a 24-hour period. And you can see that, hey, it's quiet, oh, something got busy, launched more servers, shut them down. And because we're paying per minute, it makes it extremely cost effective. So how does this work? Well, ultimately, our developers don't actually have to think too much about this, which is great. You're working on building software, you don't want to think about servers and memory. So the idea is we set a requirement on every container that runs, how much CPU, how much memory it requires. When those resources start to get constrained, so for example, when CPU usage is getting high, we use that to trigger a process to launch more copies of that container. Or alternatively, if the CPU usage is low, we shut down a bunch of containers. So essentially increasing and decreasing the number of copies of a backend application at any point in time. And we can use other metrics for that as well. For example, CPU alone is always a go-to metric that people love, but it's not actually that reliable for a web application. And for example, you may have an app that takes, say, 30% CPU to run, but has got a 5-second response time. Now, if you're waiting 5 seconds for your app to get an API response, that's a poor user experience. So we scale on not only CPU, but also application latency. We also take in other factors. We pull in various metrics from our own technology platforms. We bring in stuff like the queue depth and other pressure on internal systems, and use all those metrics to decide how to increase and decrease our platform. And it actually feeds back into server scaling, because we're increasing and decreasing the number of containers, the number of applications, but we also need to increase and decrease the number of servers underneath to sustain the requirements of those applications. And it's pretty much the same thing. So we have a model where we operate on essentially a 30% buffer. So we always want 70% of our CPU and memory to be utilized, and we leave 30% spare to handle the launch and destruction of containers. So what happens is if we get to, say, 90% CPU utilization, we start booting up servers to give us a bigger buffer. If we get below, say, 50% CPU, we start shutting down systems to save us money. And this actually works pretty well in production. So the top line on this graph is the CPU utilization across a 1-month period. And you'll see that our CPU usage is pretty much sitting between 60 and 75%, sort of constantly fluctuating. But unseen on this graph is the number of servers has been changing significantly throughout that. So we maintain a consistent utilization amount on our environment. So it may seem a little bit wasteful. Jeffrey, you're wasting 30% of CPU. Like, they aren't free. And yeah, 30% is a bit. But your typical environment could well be 80 or 90% wastage. So we've gotten down to a point where we're much, much more efficient because we only launch when we need, but we're not running so tight. Like if we try to run, say, 5% wastage, we risk impacting customers because the utilization, the space available for sudden changes in load is so low, it can easily impact someone in a more negative fashion. So, okay, this is cool. Is it suitable for your use case? Well, the tricky thing is with any advice in infrastructure space, particularly in New Zealand, is it really depends because we're doing so much at different scale. There'll be many developers at this conference who are using apps for maybe 1,000 users, but there are also people here who are doing apps for hundreds of thousands or millions of users. So realistically, your infrastructure choice is going to vary significantly based on the volume you need to support. But regardless of that, I would strongly recommend if you're doing backends for your applications, looking into Docker and containerization and learning to understand these tools, because it does make it very easy to package your software. It makes it very easy to redistribute your backend application to other members of your development team. Maybe you've got a separate backend team to mobile team. It makes it easy to provide them the current version of your backend application. And the other great upside is you may be a small startup now with 2 people, but once it's containerized and you become a big successful company, with 20 people and millions of users, the technology choice is already right. You can just scale that upwards. So what platforms do you run this stuff on? Well, there's actually no right or wrong choice, really. There's nothing to be ashamed of going, you know what, we run our production backend on Heroku. Maybe it's a small application. Maybe Heroku meets your needs perfectly. Awesome. There's a good choice. Or maybe you've got more complex requirements. Maybe you need specific Amazon products or database services. So you want to be on something like Beanstalk or ECS. Or maybe you really want to go all in with Kubernetes and you're happy to take the additional learning curve and responsibility. So I'm not going to recommend a particular choice, but there's a whole bunch of good options out there, and I'm happy to chat in more detail afterwards about your specific use cases if you wish. I just want to mention serverless. So serverless, you may have heard of, is new. It's a little bit of a confusing label because you've got serverless, a framework, and you've got serverless like the ideology. So that logo is stolen from a framework. And the idea behind serverless is not that servers don't exist anymore, but that you don't have to manage them. So with containers, you're still thinking about software. You're still running like HTTP servers. You're still listening to requests. With serverless, the idea is you say, hey, big cloud provider, Google, Amazon, I just want to give you some JavaScript and you figure out how to run it. And they take responsibility of doing all that scaling and management of your application workload. So Firebase Cloud Functions is one popular option. You've also got the Amazon Lambda offering. I'm not going to go into too much details about these. There are some significant benefits if you're a small environment because you're not paying for an always running server. You're paying maybe a microcent per HTTP request. But as you grow, that could become either cost prohibitive or it may still be really beneficial depending on your usage patterns. So yeah, it's something worth looking into if you're doing a new build, but I'm not going to go into too much detail. So this is all well and good. We've got a situation where we've got a platform that will increase and decrease based on resource consumption throughout the day. But a daily usage curve is quite easy to predict. I know that around 4 a.m. my server's going to get busy because it's the US daytime on the East Coast. So I can pretty much predict the scaling pattern that's going to occur. And it's quite organic. People wake up, they get on their phone, you can sort of see the traffic climb. Some aspects of our product have made that a little bit harder because we do push notifications. And our pushes can be big. So we have a lot of customers, and many of these customers have user bases approaching maybe 15 million for a single application. Now, if they want to deliver 15 million push messages in, say, under 30 minutes, that's 500,000 per minute, or around 8,300 a second. That's actually quite a few messages. We've got to go fast. We can't afford to take time, We can't send messages for 12 hours. We've got to get them out. So can FCM and APNF even scale? Well, it's Google and Apple. Like, what do you think? Can they scale? They can probably scale. So there's a bit of responsibility on your side. APNF and FCM will shift a lot of messages very quickly as long as you engage with it properly. Small environment, you can pretty much just use the off-the-shelf references, interact with it, no problem. Because of our size, we're going to do a little bit of optimization. So the good news is you don't have to do any weird protocols. There's no protobuf or custom UDP protocols or anything funny like that. It's just bog standard HTTP. But to get the speed on our platform, we had to engage with the providers using HTTP2, which has a whole bunch of performance advantages. The trade-off is HTTP2 is still new, and it can limit your technology options for this a little bit. One of my colleagues, Adam Jones at Salfro, he wrote a really awesome open source library for interacting with APNS using Golang. And we've actually found that library is capable of delivering up or at least 100,000 push messages per second. We don't know how much faster it could go, like we kind of got bored at that point. But it's really fast. And in fact, a few of our competitors have started using this library, so it's kind of like, it's pretty cool. Every time we see like an issue or a PR from them. But this is only half the problem. I mean, sending pushes quickly, it's just about managing HTTP connections outbound, having connection worker pools, that kind of stuff. It's only half the issue because we collect telemetry from all of those cell phones that we're sending stuff to. So when you blast out 15 million messages in, say, 15 minutes, all of a sudden you have a whole bunch of phones waking up going, hey, I got a message, and then a user engaging is sending traffic all the way back to our servers in a very short period of time. And suddenly we have a traffic graph that looks a bit like this. Now, we can scale. I mentioned before, we've got containers, we've got auto-scaling, and we have that 30% buffer. But it's 30%. It's not a 200% buffer. We can't just triple the size of our infrastructure in 2 minutes flat. So that was a little bit of a problem. And it actually wasn't a problem unique to our backend. We actually had multiple customers going, oh, you're sending too fast, we can't handle it. Because not only would the phone send telemetry back to us, it would send API calls back to our customers' servers, and often their servers weren't geared up for this kind of volume either. So for a bunch of customers, we did add rate limiting, but we still had customers, particularly media customers, who really want to be first to file a news story. So these customers, we said, we love the speed, we want to go faster. And we're like, well, okay, how do we solve that? Well, we developed a tool we call the push scaler. So this actually became possible because of the nature of the organization that we're in. I have a very close relationship with our development team members in that I sit with the developers, we work on the same product, I bring infrastructure skills to the team, they bring development skills to the team, and combined, we're actually competent at doing something. So the upside of that is I have a basic understanding of what the software does, and they have a basic understanding of what the infrastructure does. So to solve this particular DDoS problem, we realized that we could actually integrate with the backend platform that generates the messages and automatically start launching more servers as soon as we detected a large outgoing push message. So this is a diagram showing it live in action. So this is a little bit hard to read, but if you look at the bottom left corner where it says a push is sent, that graph shows a big spike when pushes started going out of the platform. And then you can see on the top graphs, we started launching more containers and launching more servers before the corresponding spike in requests came back into our system. Because we know it takes 90 seconds to launch a server. If we know exactly how many servers we're going to need, we can pretty much boot everything we need in time for all the requests to start piling in from users. And this is working really well for us in production. This has saved us many, many times and results in a really high performance system for customers without wasting a giant pile of money running way over capacity. All right, cool. Let's say you've done this. You've built your awesome containerized platform for your backend application. You've got push scalers and other magic. But how do we actually get software onto this backend platform? I mean, we don't have an app store. Like, we're backend people. We have to do it ourselves. I mean, it's faster. Don't get me wrong. There's no waiting process. Apple can't say no, which is great. But we have to do the work. So if you're still familiar with FTP and you still use FTP, I'm sorry, it's dead. There'll be a wake for it at Milk and Honey at 5:30 p.m. today. Instead, we have continuous delivery pipelines, or sometimes referred to also as continuous deployment pipelines, which is a whole argument we could have another session about. But the general premise of this technique is that code should always deploy itself when it's ready to go out. So it's really the dream of being a developer. The idea is you push your code to GitHub, it releases itself, and then customers will pay their large invoices on time the same day. And the good news is two out of the three of these things are actually possible to achieve right now. So the way this works is you still tend to have some control. It's not just YOLOing, pushing stuff straight from your laptop into production. So there's a really popular design pattern called Git flow, and the principle of Git flow is When you're working on code, you work in a feature branch, you then merge it into the develop branch, which maps to your pre-production or your staging environment. And then when you're happy that it's safe to go out, you merge it to your master branch, and then that automatically deploys out to your production systems. We've actually taken a slightly modified approach of this at Sailthrough, where we have our master branch going to staging and pre-prod, and then we tag a release when we want it to go live to production. And it's just because we found it made it really obvious when you're doing a production deploy. You couldn't accidentally merge something to master and go, oh, whoops, that went live. And it also reduced some of the pain of having to sync, develop, and master branches. If you've ever worked in a large team, there can be a tendency for people to merge a feature branch into develop and then leave it there. And then it's like, is this safe to release? And people are like, oh, maybe. And it becomes really hard. So this is the pipeline that we utilize at Sailthrough. So the idea is that we push our code to GitHub. GitHub then invokes our build system. That goes and grabs the code, runs all the unit tests, we run integration testing. This is one of the upsides again of being Dockerized, because all of our different backend services are in Docker containers. Every time we build a single component of that service, we can launch all the other containers and do integration testing using the real software. So we don't have to mock the different backends, we can just run the legitimate backend and test it. So we do our build, we generate a Docker image, and then we combine it with our configuration for a respective environment, staging and production, push it out, and then we tell Slack. So for your day-to-day developer workflow, it is pretty much hit release in GitHub and then see the message come into Slack, which is fantastic from a developer workflow perspective. You don't have to go, hey, ops team, what's happening with the code? Is it rolled out yet? You're not watching a bash script SSH onto server 1 to 20. You just hit a button and sit back and relax. I mean, yeah, sometimes you might push a bug to production and we can just use the same techniques to roll it back. We log all the versions so we know exactly when we upgraded. So if we go, oh look, the graphs are showing a performance degradation as of 10 AM, you can go back to Slack and go, oh, 10 AM, we released that new version. Maybe that's what it is, it's revert. And we also track like the configuration values that are changed at what time they change, because that can of course change the behavior significantly of your program. And this isn't unique to our backend infrastructure. We do the same thing for our mobile SDKs. So we use a completely different pipeline because Xcode's less than ideal. So we use a company called Bitrise, and they're a hosted service that do builds on actual Macintosh machines, and they use Xcode command line tools to do the builds for us, and that makes life so easy. And they deserve to shout out too, because they sent me a Christmas card with stickers once, so I actually really appreciate that. Every other vendor sends me a bill, so I like these guys. I mean, they send me bills too, but... So why do we care about this? Well, but making your releases easy to deploy and release is critical to making your life is critical to achieving better results as a team, because you can deploy bug fixes almost immediately. You can deploy features when they're ready. So instead of going, okay, we've got to bundle up all the features for the sprint, and at the end of a sprint, let's do one big bang 2-week release. You can just go, oh, feature's ready, peer reviewed, checked, product likes it, check, release to production. Hey customer, that feature you asked me about is now live. It's super quick to give feedback to your stakeholders, to your customers. Not only that, it frees up significant time. I mean, if you're spending a couple of hours every week doing releases the hard way, building a pipeline like this suddenly gives you a whole bunch more capacity you can use to actually build software and do the things you care about. Unless you're weird and like me and you care about deployment infrastructure, in which case, maybe you like that. You've probably seen a whole bunch of these different technologies. There's a shit ton of different options in this space. These are probably some of the names that you actually recognize. Again, the right tool depends on what you're trying to do. And you're starting to see like a little bit more convergence with platforms integrating these tools natively. Probably the best example is Heroku, where it's literally fully tied into your repository. But also GitLab work this way in that GitLab provides you a GitHub-like source code hosting system, but also provides you a deployment pipeline service in itself as well. So, okay, let's say you've done this. You've got your containers, you've got your pipeline, you've got magical auto scaling, you're pretty much ready to go, right? Well, oh boy, you're only just getting started. The problem is, we've only been talking about applications so far, and most applications tend to want some kind of data. So, applications are pretty easy to scale because we're not worrying about attaching state. If we need more web servers, we just turn more web servers on, they talk back to the database which stores the state. But what that means is your database is now a bottleneck. I can launch 10 copies of the app and I have 1/10 of the work happening on each box. I can't just launch 10 copies of the database in most situations. Generally, it's designed around the concept of a singular server which is performing all the writes. So I'm going to prefix this by saying DBAs actually have a really hard job. And if you're not a DBA, you probably don't want to try and be one. You've got enough problems in mobile. So use managed services where you can. So when I mean managed services, I'm talking about things like if you're on the Amazon platform, using Amazon RDS. If you're on Azure, using the various Azure SQL offerings. Because a lot of these products that cost a little bit more than just doing, apt-get install MySQL, they generally make it really, really easy to get a reliable production-grade system. So what they come with is they come with high availability. They come with an easy option of upgrading your servers without causing any significant downtime. And surprisingly, they have backups that actually can be restored. Very, very handy when you're running a production product and you're not a DBA. So I'd strongly recommend, no matter what size your org is and what size your product is, look into using a managed service to store your data. And there's a heap of options in the space. I mean, we've got all the traditional SQL choices, as well as a whole bunch of the NoSQL options that now exist as well. And it's not as simple as NoSQL is better because it's newer or SQL's old and crafty. They actually have their own distinct use cases, and it still applies. There's also a few generations of newer products that sort of sit in weird spaces. So if you've not heard of Amazon Athena before, it's got a SQL query language, but it reads data from JSON files in an S3 bucket. So it's like, is it SQL? Is it NoSQL? I don't know. It's kind of both. So why might you want to use a different database technology, say NoSQL versus SQL? Well, one thing SQL doesn't do very well is it doesn't shard very nicely. So if you think about a database server receiving a large number of write requests, at some point a singular server cannot keep up with that write volume anymore. With a SQL database, it can become quite difficult to shard that off and say, hey, send half the writes to this server and half the writes to this other server. The NoSQL offerings such as MongoDB make it really, really easy to slice up your data across a number of servers. So an example of that would be, let's say you've structured your database so that everything's got a specific application ID. You could send one application ID to a different box and then slice up your workload in that fashion. And this is actually really critical to our environment because we operate a MongoDB cluster with 4 shards, each shard consisting of 3 servers, a primary and 2 secondaries. So a total of 12 servers operating in our environment. We would be unable to achieve the volume that we are doing with a singular SQL database, or even a singular MongoDB database, because the write volume we perform from all those devices constantly phoning home is so high, you start reaching actual locking limitations in the database technology itself. So I can throw more CPUs, I can throw more RAM, I can throw more money, it won't get me a faster database. I have to slice up our workload, shard it across multiple servers. So am I saying it should use NoSQL? Well, like anything, it depends. One of the biggest differentiators would be around transactional guarantees. So if you're building an application, say a public transport payment app, users generally get annoyed if you lose their payment. Oh no, you haven't topped up. Oh mate, I put $50 on it. Like that gets very, 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 very irate, strangely enough. SQL databases are very good at transactions. You know exactly whether it's committed or you know whether it failed. There's no, you can enforce it one way or the other. There's no halfway, I kind of updated state. It's all or nothing. NoSQL databases tend to not necessarily focus on the accuracy so much. They're pretty accurate, more than good enough for analytics and metric tracking, but not necessarily for the absolute critical precise transactions that you might need for some other workloads. And the other consideration is going to be around the other technology choices you make. So when we think about traditional databases like MySQL or Postgres, typically you're running them on a virtual machine. So you're already paying your $50 a month to run your VM. But then if you built your application in a serverless stack where you're paying per request rather than a fixed fee, maybe that becomes cost prohibitive because you've got a small app and you want small volumes of requests. It might make more sense to use something like DynamoDB or Firebase where you're actually paying per request to the database. So everything's kind of like a free market user pays model. A request comes into your Lambda, you pay for a request, it goes to the database, you pay for the database request. If your application has no users, you don't really pay for anything. It's quite a nice model when you're very, very small. The other big consideration is going to be around the design of your backend application. So, for example, our application is mostly a real-time system. If you engage with like one of our customers' applications on their phone, it triggers an event to us. We receive that event, we process that event, and we update the database. 1,000 events, 1,000 database updates. And this isn't just a technique to allow us to pay Amazon or MongoDB lots of money. It's actually a feature our customers desire. They want to be able to interact with their phone and see it immediately update on graphs and on metrics. It's a nice user experience, but it's also an expensive experience in terms of processing overhead. Whereas if we say we're to move to a batch processing model and just collect all the events for a 1 hour period and then do some roundups and then do a single database update, we could, dramatically reduce the number of databases that we have or the size of databases we have. And these are things you can consider when you're building your platform. Does it make sense to go down a particular technology path and influence the requirements you have from there? I'm going to do a little bit of a plug for APM tooling. So if you're not that familiar with backend development, maybe your true love is mobile and backend is that filthy thing you have to do to serve JSON files to your app. Well, the good news is you can kind of replace half of a DevOps engineer with these tools. And yeah, these tools are a little bit expensive, but a DevOps engineer, as good looking, as modest as myself, is also kind of expensive. So the cool thing about the software is you drop the library into your backend application and it abstracts all the details about what's going on. It can tell you, for example, that you spent 32 milliseconds in a particular method. It can tell you exactly how slow your database is on a particular query. It can tell you what that query was. You can do things like, for example, tell you which HTTP services you're interacting with, which are slowing down your application. So if you're running a backend system and you don't have heaps of in-house guru engineering skills to trace applications and figure out what's going on, these tools suddenly become very, very worth the money that they cost, because you can drop it in and immediately get the basic debugging information straight out of your application. And I mean, it's also not even that an engineer like myself doesn't require them. I mean, we use these tools constantly in my day job because this can tell me in 5 minutes what's going wrong with the platform, as opposed to the old-fashioned days when we'd chuck a debugger on it and spend an hour figuring out what's going on. It means that I can focus on more important things of my time. Okay, so let's say you've done that. We've done all the cool stuff we talked about previously. We've built scalable apps. We've got a scalable database. What else do you want to think about? Well, your platform choice can make quite a significant impact to your infrastructure. So we started off as a small startup, like most companies, strangely enough. And we started off using Ruby on Rails because it's a really, really lovely framework. We've got lots of developers who enjoy writing in Ruby. It's got great testing suite. It's just nice to use. But Ruby developers are nice. It's great. It's a great community. The only problem with Ruby is it's not the most efficient platform at high scale. So we burn a lot of CPU time and a lot of memory running these Ruby applications. If we were to, say, rewrite it in Java or Elixir or Golang, we could significantly reduce the amount of compute we operate on. But then you've got a trade-off problem. And so for us, we had a discussion, which is, does it make sense to stop developing product for 3 or 6 months to port to save Amazon costs? And ultimately, it's going to depend on your size. I mean, I can probably save 10,000 USD a month if we fully ported everything to another platform, but that could cost us multiple millions of USD in terms of lost time developing features and failing to get deals we need with our customers. So that kind of game where it's like, is it worth changing or not? And this is something you have to reevaluate as your backend platform grows all the time. Is your technology choice still relevant? If you change to a faster technology, how long will it take you? Can you hire the people you need? I want to talk a little bit about microservices because microservices are really cool. Everyone loves microservices. But these came out of companies that were really, really large organizations with hundreds of staff. Spotify, Google, Netflix, those kind of companies. They're not necessarily suitable for your two-person startup or your singular purpose application. So if you're building a single backend for a single app, you probably don't need one. You can just build a Rails app, you could build a Spring Boot app. Sweet, keep it simple. There's no benefit to being complex if you don't need to be. I mean, even in our environment where we've got a lot of different components, systems doing background analytics generation, systems focusing on very specific requirements, I can probably still count the number of services we operate on 2 hands because we don't need to separate everything out where it doesn't make sense. There's a really good post that I'd like people to read if you haven't read it already, which is called The Majestic Monolith by DHH from Ruby. And it talks about this principle, which is it doesn't make sense to separate your application into chunks that run independently if they're always going to be running together anyway. And then you might not agree with the premise, but it's definitely one to read and consider. All right, I want to do a little bit APIs. So our product started off as a marketing product where teams could use the UI to send messages. As it evolved, we had more and more developers going, hey, we like an API, so we provided a public API. Turns out developers like to use APIs. And even if you don't provide one, they'll find one, just like searching GitHub for any Metlink API will tell you. And regardless of whether you intended to provide the API or not, the customer or users will always surprise you with what they do with that API. So we've started using a technique for API rate limiting, because we had a real big problem for a while where customers would start using the API and then slam it so aggressively it could negatively impact other customers' experiences. And I'm fine with a customer getting to a position where they're struggling because they're doing something odd, because we're happy to help them and support them through that process. But if they're causing disruption to other people, that's really, really serious to us. So if you are building an API, specifically an API for customers to be consuming and interacting with, I would strongly recommend you build API rate limit controls per customer, not combined, because it allows you to grant a particular customer a higher limit or lower limit than another customer. And in fact, this is used quite a lot by some of the big cloud providers. If you've ever been using Amazon in any significant way, you've probably run into the dreaded service limits problem. Oh, you can only have 10 policies on your IAM role. Well, fuck you, Amazon, I want more than that. You have to go file a support ticket and be like, hey, Mr. Amazon, can I please have 11 security policies? That's their method of, again, making sure they don't get surprised by what you're doing as a customer. They expect you to have a certain reasonable limit, and then as you start getting to the limits of that, excuse the pun, they will grant you a higher threshold. So, like I was saying, you need to be per customer, and you just make sure you feedback this limit to a customer. I had actually had a discussion with the technical team just this week, where when you reach a limit, they just throw you an error code. I'm like, well, that's not very helpful. Like, what does 500 mean? That's not very useful. 429, the standard response code for rate limiting, is much more useful. And also monitor it. You kind of want to know if your biggest customer is hitting limits, so you can proactively reach out to them and figure out what needs to happen. So, well, I know, sorry, there's heaps of information, heaps of stuff in this presentation. I'm more than happy to meet afterwards to chat more about any part of this or infrastructure in general. I mean, pretty much any part of this you can talk for an hour about, so come meet me afterwards, happy to deep dive any particular component, talk about your requirements, or talk more about some of the stuff that we've run into in our production environment. But yeah, thanks for coming along. Feel free to check out my blog. Feel free to check out Selfie as well. Like, we are hiring in Wellington. We're always interested in back-end people, front-end people, support engineers, that kind of stuff. So come see me if you're interested in that sort of thing as well. And yeah, thank you so much.